I'm a physicist. I have a PhD in solid state physics, and I work in research for a private company. And I'm basically working on healthcare sensors. And I do this stuff, which is astrophysics or physics in general, because, well, actually I can go with the next slide, because I like to popularize science in Romanian. So I'm basically talking all the time in Romanian for Romanian people, and talking about physics in Romanian and physics in general. So I wrote these 2 books in Romanian, The Story of Physics, and the second one is on the left. And basically, there are books about physics in general. I have a YouTube channel, which is on the right, so you may subscribe if you want. Some of the videos, they also have translations. So in other words, you have subtitles in English. I can also be found on Facebook, Discord, and my email for people who want to contact me in private. But this is just a warning to let you know that I'm not an astrophysicist. So I talk basically from a general physics perspective without entering into details. And when I say the physics of compact stellar objects, don't be scared, because it's not going to be advanced physics. This is like for a general audience. And by compact stellar objects, I mean the objects which actually happen when they come at the end of the lifetime of stars. And there are 3 objects I'm going to discuss: white dwarfs, neutron stars, and black holes. And there are going to be 3 sessions, and this is the first session on white dwarfs. I have to admit that I wasn't aware that you are going to put on Facebook, so I have some images here which I taken from YouTube, but I hope there is no problem. And I have acknowledgements in the pictures or on YouTube when I have. But this is just my introduction with the kind of type of stars. I have to check actually also my time, because I don't see it here. Okay, that's good. And by the way, Alex, just be aware, I'm not able to see right now. Maybe if I do like this, I'm able to see the chat. Because
I can see the chat.
Because I don't see the chat, so if there is something, you have to tell me if somebody wants to put a question.
If you check on the bottom line, you'll need to find in that place participants when they chat screen sharing.
Yeah, but there is.
Did you find it?
Let's say a practical problem, because I have the PowerPoint in the presentation mode, and it just jumps up on my whole screen, so I'm not going to change it.
I'll keep an eye on the chat for you, and if I see somebody can type a question, or Alex, you'll see someone raise their hand.
Okay, that's the point. If someone want to talk, I will.
Yeah, because I don't see the chat because I have the screen full screen.
If someone want to talk to you, want to say something, I will announce.
Actually, that's kind of, I have to do it next time to be able to see the chat. One moment, because I usually like to interact with people, and it's indeed quite.
Oh, that's a beautiful image.
Yeah, but I know I'm not able to see the chat in this particular view, which I have on the computer. So, okay, that's it. So basically, these are all, some of the stars we see on the sky. We have red giant star, We have the red supergiant star, blue giant star. And we sometimes see when we look at the sky that they have different colors. And usually the stars which have colors, which are either blue or red, they are big stars. And we have Betelgeuse, for example, which looks red because it's a red supergiant star, if I'm not mistaken. And we have Nigel, which looks blue, which was also kind of a giant star. And people try to put the stars, say, well, how can we order the stars? So what we see here, we see the HR diagrams of stars on the left side and the same diagram on the right side. And what is very, very important in this diagram is the temperature on the bottom scale and the luminosity on the left scale. So what you see here is that most of the stars are in the middle. For example, sun is somewhere here, more or less close to the center when I show my mouse. And the bottom line is also colored because when the star is blue, they have a lower temperature. Whenever the star has a higher temperature, then it becomes more red. So when you look at the sky on, in the night, and you see a red star, then you may say, well, actually, that's a cold star. If you see a blue star, then you may say, well, actually, that's a hot star. It's the other way around, how you would expect. And so most of the stars are on this main sequence, but every star has a life cycle. And what you see here on the right is the life cycle of the sun. Well, the sun starts here and it burns most of the hydrogen, becomes helium. And at one point, the star becomes larger and larger. And I'm going to explain you why, but I can tell you that this is because you may think like this: the star burns the hydrogen, so it becomes a little bit hotter and hotter. So in his lifetime, the star becomes hotter with about 30% until the end. And when it's hot, it starts to have more pressure inside, and it's going to push the star. So the star becomes larger. So that's why the star increases also the sun. So it's going to increase the sun. But anyway, it's going to become at one point a red giant. And after the red giant, actually the sun is going to become a white dwarf, which we have here on the left bottom. And then I'm going to discuss about white dwarfs. This is actually a picture from my second book, which has some nice drawings. And there are some writings in Romanian, of course. And basically this summarizes what I'm going to talk about in these three parts. What you have here, you have a nebulae. Every star starts like a nebulae, so a lot of hydrogen together, and it starts to fuse hydrogen inside. And when it starts to fuse hydrogen inside, it either become a star of medium size, which like the sun, depending on how much hydrogen it is, or a very large star, like a blue giant here. The sun is called actually a yellow dwarf, so it's actually one of the smallest stars. And that's what you see on the top part. So at the end of the sun is going to become larger and larger, it's going to become a red giant, and then it's going to shed out the outer layers, as I explained, and in the center is going to remain a white dwarf. That's what you see here on the top. And the white dwarf is going to become a black dwarf. So this is the subject of this presentation. Now the bottom part is going to be subject of the next things. So first of all, we have the nebulae, and from the nebulae you have this time a large star because there was a lot of hydrogen. And the large star is going to become even larger. Okay, hopefully I have no crash in the computer. And then at the end of the day, there is a supernova explosion, so it's quite different. And in the center, you are going to be left either with a neutron star or with a black hole. So next time I'm going to talk about neutron star, and the third time about black holes. Okay, now I have here a presentation. I took it from YouTube just to see, because usually this is YouTube and internet, and on the internet you have all kinds of nice presentation. So in my opinion, it would be a pity not to use it. And what you see here is the sun becoming a red giant. And of course, they say that it's going to swallow Earth when that's going to happen. Okay, so let's go to the next slide. And it's not the next slide. Let's finish this presentation just to avoid crash. Okay. Because I have another presentation, and this is actually a presentation with what is going to happen with the sun at the end of its lifetime. So what you see, you saw the sun becoming larger and larger, or a different giant, and then exploding. And in the center, there was a small star left. You see, exploding, exploding, and at the end, a small star left in the beginning. Okay, actually, we do see these remnants of the red giants after explosion on the sky, and one is very close to us, and it's called Sirius B. Sirius B, it's the sister, or the brother if you want, but I think it's a sister in English, of the largest star Sirius. So when you look on the sky in the night, you see a bright star, and one of these bright stars is actually Sirius. And Sirius has a small companion, and that companion, which you see here in the visible spectra, with the visible telescope, is actually a white dwarf. And you also see it in X-ray spectrum. So these things exist, and we measure them. And this is a beautiful picture, actually, with the white dwarf in the center coming from the ring nebulae. So what you see these bright colors, and these bright colors are the layers which were shed out by the star, by the red giant when it exploded. And what you see in the center, the bright dot, is a white dwarf. And another one, but this actually is not yet a white dwarf. So the star which you see in the center is going to become a white dwarf. That's the Spirograph Nebula. Very, very nice picture. Now I put here some formulas, and because I told you it's about physics a little bit, but the thing actually you have to remember is the right part. The right part tells you that when you look at the color of the star, you can guess the temperature. And you see the stars on the bottom, which are kind of yellow, they have temperatures of around 3000 degrees. And you see the stars on the higher part, now on the top, which are bluish. They have a very high temperature, like 27 degrees. Now, how do physics know, how do the physicists know actually that the higher the temperature, then the star becomes more bluish? And the relation is actually on the left. So what you see here on the left, you see here a spectra which is sketched by my hand, something like this. So you see the intensity of the light, but measured by a spectrometer for different colors. So this is the frequency of the color on the bottom line. And I hope you see my mouse, because otherwise I would have to put the laser gun, but I'm going to look into it now. So basically what you see here is the spectra measure of the star. So for every color, which is on the bottom, you see the intensity, and there is a maximum. And that maximum actually tells you what the temperature is. And how is that? Well, you can use this very simple approximation, because this is not very, very precise physics. This is just an approximation. And it tells you that the energy of the photon of that frequency, which is HF, is the Planck formula, actually that is equal with the average energy of the degrees of freedom, which is K, where K is Boltzmann constant times T. So in other words, if you take the spectrum, measure the maximum, you use this formula and find out the temperature. And that's why when the frequency is larger, so when the frequency is larger is here, that means you see that the star is blue. Then the temperature is higher. And when the frequency is lower, which is here, that means red, then the temperature is lower. But this white dwarf, they had a kind of mystery right from the beginning. And the mystery was the following. Well, actually the star is white, so it's kind of has a higher temperature. It's not cool. It has a higher temperature. And if the star has a higher temperature, it should have a lot of luminosity. And so the star should be basically very bright. And you look at the white dwarf, and they are not very bright. They are not at all bright. And you may think, okay, maybe the white dwarf is not bright because it's very, very far away. Well, it is not the case because the star is very close. We know it from Sirius. Sirius is few years away. And still, the white dwarf is not very, very bright. And that was the mystery. Why was the white dwarf, even though it has a high temperature, not bright on the sky, even though it was very, very close? And the answer actually lies in another formula, which I like. I like physics when you have these small formulas and you try to estimate stuff. But the idea is the following, that without measuring with a telescope the size of the star, you can still estimate the size of the star based on the luminosity. So you can estimate, so in principle, we can estimate the size of white dwarf without actually imaging and measuring the size of the white dwarf. And that I really, really like. And the way the astronomers doing is using this formula of Stefan Boltzmann law. Now, if you do a little bit of thermodynamics, you know about a little bit about the emissivity, which is this part here, sigma T to the power 4th. That tells you if the temperature is very, very high, then you have a lot of emissivity, a lot of light. It's like the fire becomes hotter and hotter and hotter and becomes brighter and brighter and brighter. So there is a lot of emissivity, a lot of photons, a lot of light which goes away. Now, how bright is the star is actually given. So how bright is the star? I call it here absolute luminosity. So no, not how much it looks on the sky. No, but how bright is the star if you would be close to the star? So the absolute luminosity. So the absolute luminosity L here is actually the product of two things. First, the emissivity, which is sigma T to the power 4th, and then the area. So the size of the disk of the star, you know? And then remember, the white dwarf had a lower absolute intensity light. How is it called again in English? The absolute, absolute intensity, I think. No, it's not the right word, doesn't matter.
The luminosity, the absolute
luminosity, yes, here, the luminosity. I'm so much
yes.
I'm so much using it, in terms in Romanian, then it's luminosity, of course.
It's similar in Romanian, yeah.
Yeah, it's similar, luminositate, indeed. So it's actually the luminosity. So then again, we know from this formula that actually the luminosity is very low. That means that the area of the disk is very, very small. And using this formula, the astronomers could indeed estimate the size of the white dwarf without actually measuring it, because they measured the absolute luminosity. How did they measure the absolute luminosity? They measured the relative luminosity, so how bright is on the sky, but they knew how far away it was. And based on the distance, they say, well, the absolute luminosity is this. And they use also the temperature, which they measure with the spectra, and then they said, this should be the radius of white dwarf. Well, and actually you see it on the right-hand side. It turned out that the white dwarf is as small as Earth, more or less. So it's very, very, very small. And also the astronomers knew the size, the mass of the white dwarf. And it turns out to be more or less the mass of the sun. They knew that because of the Newtonian mechanics, how the star moves around the other star. So they asked themselves, how is it possible that you take a star like sun and squeeze it and squeeze it and squeeze it, in a star like a white dwarf, which has the sign of the size of the Earth? And the mystery, and this was a mystery in the history of physics, and actually it was solved by an Indian physicist called Subrahmanyan Chandrasekhar, something like this. I do apologize. Chandrasekhar, yeah, something like this. And then, so the Indian guy was a young guy of like 90 years of age, just in the period of the First World War. And then after the First World War, so in the 1920s. And then he figured it out. And then he sent a letter to Arthur Eddington, which you see here, which was a famous English astronomer, a friend of Einstein. And he explained this to Arthur Eddington. Now Arthur Eddington was not only a friend of Einstein, but he was famous because with the help of, the eclipse of the sun, he was able to verify the general relativity of Einstein. So Eddington said, well, I can measure that the light bends around the sun. And he did that during the solar eclipse. And because of that, of course, he was very good friend with Einstein. And Chandrasekhar went to Eddington, wrote a letter, and he sent him the equation. and Eddington found it brilliantly, so he invited the young Indian physicist to England, and actually for the rest of his life, the young physicist just became a famous physicist in England, working in Cambridge and solved the problem. Now, how do you solve such a problem? How are you able to squeeze all the mass inside the white dwarf? Well, first of all, you have to realize that inside the white dwarf, you have more or less carbon atoms. Why do we have carbon atoms? Well, first of all, you have the sun, and sun has hydrogen most of the time. But in the core, the sun fuses hydrogen to helium. And the temperature increases, and the temperature increases, and the temperature increases, stars becomes larger and larger. But because the temperature increases for certain stars, because of course the mass of the star should be a little higher, because the higher the mass of the star, the higher the temperature in the core. When the temperature in the core reaches something about 100 million degrees, then the fusion of helium starts. And then you make carbon, you know, and then you make carbon, it becomes hotter and hotter. But the outer layer went away. And because of that, you don't have any more pressure, you know, to fuse carbon. And because of that, the star remains a carbon star. It's not able to fuse any more carbon inside because the star is smaller and it doesn't have, you know, enough gravity pressure to push on the center to increase the temperature to even higher levels so that to fuse carbon. So the core remains carbon. And if you calculate, you say, wait a minute, but if the atoms of carbon and if the whole white dwarf is the squeeze to the side of the Earth, what would be the size of the carbon atoms? You know, what would be the size of the carbon atoms? And you see that on the right, and well, actually the size of the Earth is 100 times smaller than the size of the sun. So that means that the size, more or less, the size of the atom carbons inside the the white dwarf star are about 100 times smaller than the size of the atoms normally. So that's what you see here. The star has atoms, let's say hydrogen, 10 to the minus 10 meter. And the size, this is 10 to the minus 12 meter, the size of atoms inside. But why this number, 10 to the minus 12? It's still a mystery. It's still a mystery. Well, the mystery was solved by our Indian friend, because he said, look, actually, what keeps the star for not imploding even more are not the carbon atoms. It's not the fact that the carbon atoms are so squeezed that you cannot squeeze them anymore. Most important are the electrons inside the carbon atoms, because some of the electrons become free because you push the carbon atoms so much together that the electron starts to jump from one side or another. And what you have here, you have a so-called degenerate electron gas. And this electron gas is the one which doesn't allow you to implode even more than nuclei. So it's this electron degenerate gas. So the question is, okay, why does the core of the neutron star, so that the electron degenerate gas, is not able to be squeezed even more? And the answer lies into the uncertainty principle combined with some relativistic formulas. But first, let's try to understand here what's happening. So the electrons, when you start to squeeze electrons, you have a problem. And the problem is called Pauli principle. If you take, let's say, boxes, and you say, I put one electron here, I put one electron here. In one box, you can put only 2 electrons with opposite spins. You cannot put 2 more electrons if there are only, let's say, 1 energy level. So when I say a box, I mean just 1 energy level for the electron. So if there is only 1 energy level, you cannot put 2 electrons. So in other words, when you start to squeeze the electrons cannot be squeezed anymore because of this Pauli principle. If you take the electron from one side and put it on the left side, then you would have to put the electron on the same orbital or the same energy level. I use simple words here. And then you would have a problem with the Pauli principle, because Pauli principle allows only for 2. But of course, if you have 2, you cannot put a third one. But I'm going to simplify this one here. And I simplify in this drawing here. So I don't discuss here about the spin, but I discuss only about the boxes. And this is kind of box what you have here on the left side. And this is the box. And the question is, okay, how small can you make a box to put the electrode inside? This is the question we have to answer. How small is the box? to be able to put to keep the electron inside. And the answer is actually given with the uncertainty principle, because when you know the position of the electron very well, then you don't know the momentum. So the momentum is very high. So the velocity of the electron is very, very high. So then the electron wants to get out. So the more you have electron in a box, you know, and the smaller you make the box, the larger becomes the speed of the electron and its tendency to escape. So the pressure is even higher. And on the top here, you see kind of small estimation here using the uncertainty principle, because of course, if you take the box, you can calculate the wavelength, and the wavelength is the size of the box, you know, and the momentum of the electron is given by the h of the wavelength. So that means that if you try to estimate what would be the momentum of the electron in a box of the size delta x, then the momentum would be h over delta x. But something very, very happens, something, let me see here. Okay, so here in the second part, I want to discuss about another limit, which is different, which is called the Compton limit. So in other words, if you take only the non-relativity physics, then you can make this both smaller, 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 smaller. Now what happens, and this is coming with the second formula, is the following. When you squeeze the box to a certain length, which is the quantum length, which is lambda c here, then the momentum of the electron and the energy of the electron is so large, it becomes larger than 2 times the rest mass of the electron. And that electron then can create electrons and positrons. You see? So then if you squeeze the box and put a lot of pressure into it, then the electron has so much energy that it's going to create other electrons. And this is what I see as a limit, more or less. Now it's debatable, because this argument is kind of squish, you know, it's not physics, perfect physics, but it just tells you that when you reach the quantum limit of the electron, that's the limit when the things are going to change. This electron degenerate gas, this is going to cease to exist like the gas we know, because then the energy is so much, then, you know, you create electron and positrons, and then a whole new physics is going to happen. And what I show here on the left is how you calculate the quantum wavelength. And of course, the quantum wavelength, as I said, you can calculate it by basically, let me see, I say it here, yeah, the energy is 2 times mc squared. So the energy of the electron, when you squeeze the box, should be 2 times mc squared. But on the other hand, the energy of the electron is hf here, which is h divided by h lambda. And by the way, I use this formula for a relativistic electron, so I ignore the mass more or less at this value. So if you take this formula here and this formula here, you get more or less the size of the quantum length. So what do we learn from here? Well, actually, from here we learn that when you squeeze the electrons, so that each box of the electrons is more or less the quantum wavelength, then a new physics is going to appear. So that's a kind of limit. Okay, so this is actually the size of the white dwarf, which I calculate again, because wait a minute, this I forgot to tell you. What is the quantum wavelength of the electron? Well, actually, it turns out that the quantum wavelength of electron is just 10 to the minus 12. It's precisely the number which we estimated here. So when we estimated the size of a white dwarf, we said, well, actually, the atom of the carbon should be of the size of 10 to the minus 12. And what do we have here? If we take the quantum wavelength of the electron, we have 10 to the minus 12. So that means this is precisely the physics. It just tells you that when the size of the boxes of the electrons is of the order of 10 to the minus 12, so 100 times smaller than the size of the atoms, you have a new physics. Well, that means indeed the size of the white dwarf should be more or less 100 times smaller than the size, the radius of the sun in this particular case. So that's why if you take the radius of the sun, you know, 500,000 kilometers, you get more or less the radius of the dwarf. So this is basically the physics. It just tells you that when you have the white dwarf, the size of the boxes where the electrons are on the size of the quantum wavelength, and you cannot squeeze it more, because if you do that, you enter a new physics. let me see how I say with the time. And from this, of course, you can also calculate the density of white dwarfs, which is not that difficult. So I did it here for you on the left. You say, well, I take the hydrogen atom and I have the radius of 10⁻12. I take my box of Compton wavelength, 10 to the minus 12. So it's 100 times smaller. That means that the volumes is going to be squeezed 10 to the power 6. That means 1 million times smaller. That means that the density is going to increase 1 million times higher. Now, what is the density inside the sun? It turns out that is more or less the density of water. And what is the density of water? Well, actually, every decimeter, cubic decimeter, something like this, you have about 1 kilo. That, when you buy, milk, more or less, you buy milk, it's 1 kilo, and it has 1 cubic decimeter. Now, if you take a white dwarf, and put it in this, 1 decimeter cube, so if you put it there, then you would have 1 million more times. So you have 1 million kilograms. That would be 1,000 tons. So in other words, if you buy 1 liter of milk from white dwarf material, that would be 1,000 tons. That would weigh 1,000 tons. And what you see here on the right is somebody estimated how heavy would be the material from the white dwarf if you put it into a spoon, and it gets 15 tons, which is indeed amazing. Now, of course, the physics is much more interesting, because what happens is that we discuss here more or less what is the approximate size of white dwarfs. It doesn't tell you, it doesn't tell you what the real size is, because we make the assumption in the beginning that the mass of the sun becomes a white dwarf. So this is just empirical, some kind of arguments, but it's not really physics. Now, the physics is you try to understand what is going to happen with a white dwarf if you start with stars which are larger and larger and larger. And this is the funny thing, because when you have a star like on the right hand side, which has a mass of 0.4 solar masses, so you start with the star which is smaller than the sun. It has a smaller mass, it becomes a white dwarf. And he said that it has a certain radius, like this one here, looks like Earth. Now you take another star, which is like this one here, 1.2 solar masses. So it's larger, it has more mass than the previous star. And you squeeze it and you squeeze it and you squeeze it, let it become a white dwarf. Now is actually, the white dwarf is going to have a smaller size. That's what you see here, you see on the left. So even though the mass of the white dwarf is larger, because it comes from a larger star, even though the mass of the white dwarf is larger, the size is smaller. And it's kind of counterintuitive. How is it that the size is smaller, So why is that? Why is that? It's very interesting physics. Now, the point is that if the star is very large, it has a lot of mass, well, that mass is going to push on the electrons more and more and more and more. So those boxes are going to become smaller and smaller and smaller, the more mass you have in the white dwarf. And because those boxes are smaller and smaller and smaller, then the white dwarf is smaller. And that's very, very interesting indeed. And then this is actually a famous result, but this is actually a lot of physics here. So I have only 15 minutes. So I say this very, very, very small, very short, this one here, without entering into the details, because what we discussed here when we discussed about the Compton box, so the boxes of the electrons which have Compton wavelength, we discussed that at that distance, when the size is 100 times smaller, or the size of the atom is 100 times smaller, then there is a new physics. And this physics is actually discussed by the Chandrasekhar, so the Indian guy. And then the physics, what you see here, is here on the right. Because he said the following, look, when you try to push the star, push the electron gas, the electron boxes become smaller and smaller and smaller, and they put more and more resistance, more and more resistance. And this is what you see here on the bottom line. So you squeeze the star, you go to the left, you squeeze the white dwarf, they put more and more and more resistance. But at one point, exactly at the quantum limit we discussed, relativistic physics starts to be important. And because relativistic physics starts to be important, you see here, the resistance of the electric gas decreases. So because of this relativistic effect, the electron gas is not anymore so strong to keep the gravitation. So in other words, if you take a heavier star and you squeeze it and you squeeze it, or let it squeeze, let it squeeze, let it become a white dwarf, if there is a lot of gravity, at one point the electrons are going to become relativistics, and when the box sizes is about the quantum wavelength, then their resistance is going to be smaller than it was before. And because of that, if you have stars which are 1.5 solar masses, actually the degeneracy is not any more strong. So the electron pressure is not going to be strong, and the star is going to collapse even further. Even further. And that's what we're going to discuss in next time when we discuss about the neutron stars, But this is I like it very, very much. Why? I wrote it here. Look, if there would be no relativistic effect, then you would have the curve here, which is linear and would be linear on the top. So in other words, if there would be no relativistic effect, the electron gas is going to be able to hold the gravity for all sizes, all masses. So you would have in the universe only white dwarf. You would have no neutron stars, no black holes, because the star would not be able to collapse because the electron gas would be strong enough. But because of the relativistic effects, the electron gas is not strong enough. So then if the star has a mass larger than 1.5 solar masses, or let's say the core of the stars, which becomes a white dwarf, if the score is larger than 1.5 solar masses, then the electrons cannot hold anymore and they collapse, and the whole thing collapses. It becomes either neutron star or black hole. So that's why we have black holes in the universe. Interesting. I have actually two more things, so I'm in time. I just wanted to tell you a little bit about type 1 supernovae and the end of the white dwarf. Now, the type 1 supernovae happens when you have a white dwarf which eats the material from a different star, and because the material comes into the white dwarf temperature starts to increase. And if it increases enough, then the carbon, starts to fuel inside the white dwarf. Because, the white dwarf couldn't fuel carbon because it didn't have a high temperature. But now, because it gets more mass, then it starts to fuel in certain conditions. And then because of that fuels, it's like you fire again, starts to burn and explodes. And then you have the type 1 supernova. So the type 1 supernova happens when you have a core of carbon in the white dwarf, which starts to fuse and starts to burn because the material comes from different stars. And I have here again a video, hopefully it will work, a nice type 1 supernova. Let's see, so we have here the larger star and we have here the white dwarf. And then I have one more video and I'm finished. Okay, so you saw actually the red giant exploding. I do it again because I had actually some Romanian music on the background. So I'm going to explain you again what's happening in the video. So what you have here, you have the red giant, it feeds on the white dwarf. It creates the accretion disk, and the white dwarf now, fuses the core and then explodes. Beautiful animation, beautiful animation. Okay, and we are coming at the last slide. Not this one. Okay, this one here. Now, how is the white dwarf is going to end? It's going to end as a black dwarf, not as a back dwarf, as I wrote there wrongly. It's as a black dwarf, because again, the core of the white dwarf cannot fuse anymore the carbon. So the carbon, burns, the temperature decreases, but there's still carbon there, decreasing, there's still carbon there. And then usually such a white dwarf can exist for at least 10 billion years. And at the end of the lifetime, when the star doesn't burn anymore, it becomes black. So you have like a black carbon thing. So if you want coal in the future, hopefully you don't want coal in the future, but if you want coal in the future, you go to a black dwarf. But certainly you don't want coal. You want a different type of energy, you know. But and it's certainly not coal. It's kind of carbon. But the point is that it becomes a black dwarf, and it stays as a black dwarf very, 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 very long, you know. And then it's very difficult for physicists to estimate actually when the white dwarfs becomes a black dwarf, and how long does the black dwarf live, because we don't know the physics. It depends, for example, on the proton decay. So we don't know the physics. We just know that at the moment in the universe, we have mostly white dwarfs, because maybe very, very few % of the white dwarfs became already a black dwarf. So for us to find now a black dwarf would be a kind of new news story. I don't know if they found one. I think they didn't find one, but it would be like a big news story. But certainly you have to wait more and more to see the black dwarfs. And then the last animation with the kind of, let me see. You see the black dwarfs, you know, in front of the galaxy. I mean, kind of closing to the end of the universe and of my presentation. So now I'm able to take your, I'm able to take your questions.
I have a quick
yeah, I
question.
cannot hear you. Maybe it's from me. Maybe you have them. No, it's not
I have
from
a question, if you can hear me.
you. If I say stop share. Wait a minute. I know. I put my Romanian music on low volume.
Oh,
Okay.
a low volume.
Yes. Now I can hear you.
So we haven't found any black dwarfs because, and I'm guessing that's because A, they're hard to find and see, and B, because the white dwarfs, which will eventually turn into the black dwarfs, I mean, it takes so long to get to that moment that, you know, who knows how long,
Exactly, you have to wait.
How long these white stars have been out there. So it's very interesting. Do you feel like there's any, do you feel like that we're kind of close to maybe finding one of those black dwarfs as we're getting better at using radio frequency and stuff to kind of see deeper in space? Well,
I have to admit that I didn't check the news. So it may be that somebody else already found it. Maybe you can check it, but I really certainly didn't hear about it. But I think it's very difficult, but you don't have to estimate the power of the telescopes. The technology is evolving so rapidly, and understanding the physics and the models is so rapid that maybe, you know, some of the people who look here in 10 years are going to discover a black dwarf and then get the Nobel Prize, hopefully.
Yeah, maybe even by accident. I mean, there were 2 young students who just discovered a comet, you know, not that long ago. So I think maybe it's one of those things where when we saw the black dwarf going in front of the nebula there, where all of a sudden could be spotted or something. So I guess we wait and watch, and we keep our telescopes to the sky.
Exactly, yeah. You can also write questions if you want on the chat.
Yes. Thank you for answering my question. I'm going to mute.
Our sun, I have a question from Aline. Our sun can become a black sphere, a black dwarf. Well, our sun is going to become a red giant. And after the red giant is going to let a white dwarf. And most probably, indeed, our sun is going to become a black dwarf at the end. So now our followers, you know, after billion and billion years, when they are going to look for where the human civilization started, they're coming back here and see a black thing over there. That would be our sun in so many billions of years. And Andrea asked me, what makes the hydrogen compress hard enough to form a star? Well, actually, that's the gravity. That's the gravity, because if you have more and more hydrogen in the beginning, so the star nebula is very, very large, then the atoms of hydrogen, they still attract with each other. And the more hydrogen you have, the more they attract each other, and then you have a bigger and bigger star. So the more hydrogen you have, the larger density of hydrogen, then the larger the star will be created. And the larger the star will be created, the faster the star will burn. That's counterintuitive, because you would say, well, wait a minute, the star is large, so it's like you put a lot of wood in the fire, and if there is a lot of wood, you expect the fire to last longer. Actually, it's not the case. It's the other way around, because if you put a lot of hydrogen, the star becomes larger, the gravity is stronger, push is stronger, and then the temperature inside becomes stronger, higher, and then it burns the fuel faster. So that's why in the beginning of the universe, when there were the density of the hydrogen was large, because the universe was smaller. You know, we have Big Bang, and then the universe expands. So in the beginning of the universe was smaller, the density was larger. Then the first stars which forms, the so-called first generation of stars, they were larger. And because they were larger, you know, they burn very quickly in a matter of million years. Not billions like our sun, but millions of years. And that's very good because they burn very fast, and they created the first heavy atoms like carbon and so on and so forth, and then put it into space, you know, and then the second generation of stars appears, and they could take those atoms, and some other stars took and formed planets and so on and so forth. George asked me, so the end of all stars are either black dwarf or black holes? Well, I think that the end of everything at the end of the day is black holes, if you ask me. There is no point. It's like Stephen Hawking was saying, you cannot escape black holes, because everything decays. So even maybe the proton decays. So even the black dwarfs are going to decay, and then you have protons, and you have the thermal, protons are farther away. But if you wait long enough, some of the protons will enter the black holes. So the only winning game on the longer and longer terms are black holes. Okay, do you think of the entropy could ever be reversed? If the entropy of the universe would be reversed, so you want to avoid the thermal death of the universe, because thermal death means that you have everything disintegrated and you have only particles and black holes. And of course, some of the particles now jump into the black holes, and that's it, the end of those particles. And you want to avoid this thermal end of the universe where you have a lot of particles and black holes, and you want to revert it. I know of no way to revert it. I heard the physicist who said that the most fundamental law in physics is actually second law of thermodynamics, which was counterintuitive to me, because to me, second law of thermodynamics is mathematics, you know, it's not physics. It doesn't tell you energy is mc squared. No, the second law of thermodynamics says things get disordered and disordered and disordered. So to me, it looked like mathematics. But the guy, I don't remember who was the physicist who said it, but I really liked it. He said, you know, the most important one is the second law of thermodynamics. There is no point, you cannot escape that. So I have no answer to that. From Ariadna, can a planet orbit a white dwarf? Yes, actually I showed it to a planet, sorry, not a star. Oh, planet. Well, I think so. I think so, because our sun is going to become a white dwarf. And I don't remember what is going to happen with Jupiter and other planets, because certainly when the star is larger and larger and larger and becomes a red giant, it's going to, you know, eat, let's say, the smaller planets which are closer to the sun, like Venus and Mercury and even Earth. But I think it's not going to touch further planets like, you know, Pluto, let's say. And then those layers are going to be shed away. And if those layers don't push the planets away, so let's say like Jupiter or like Pluto, of course they are going to survive. So if you come here to Earth, you know, in let's say 6-7 billion of years, you're going to find a white dwarf, and maybe, you know, what is left over of Pluto, what is left over of Jupiter, you find that orbiting the white dwarf. How can we know the lifespan of the sun? Well, actually, these are all computer simulations, and it's not only computer simulation, but we also have calculations. The thing you have to understand is that you know the mass of the sun, and that's very, very important. And mass of the sun tells you most of the things are going to happen. Because if you know the mass of the sun, you know the gravity, you know how hard it pushes, you know how hot it's going to become inside, how much fusion is going to have from hydrogen to helium, you know the temperature, you know how many layers are going to be shed, and you are able to calculate this with formulas to see how much the temperature is going to increase, how many layers are going to be shed out. So you are going to find out actually what is going to happen with the sun. So then you are able to calculate that actually the sun is going to become a red giant in so many billions of years. Okay, Heather, I cannot hear you. We are at the end of the presentation, so you have to say stop.
Let me let me unmute. And Alex, you're still with us? Well, that was fascinating. I loved all the questions that came through as well. Extremely interesting. So maybe when our sun becomes a white star, we'll still have the planets Jupiter and beyond being able to still orbit it until it gets so compressed where it becomes a black hole, and then it engulfs everything, as black holes tend to do. So really wonderful. It was amazing to have you on. I hope we can continue this discussion. I'm looking forward to the next days and getting it out there more. I think it's a very fascinating topic. I think we're always looking to expand our knowledge beyond ourselves, and space and curiosity of space and those things bring out something so exciting in all of us. I loved your enthusiasm. It's very contagious, which is what we need nowadays. And I want to thank you so much for being with us today.
You're welcome. We see each other, I think, next week. Next day, sorry, tomorrow.
Yes. Yeah, tomorrow for sure. Okay. All the best, everybody.
Okay.
Hope to see you in the next conference. Bye-bye.
Bye.